So when we're thinking about solving differential equations, at the end of the day, it's basically doing an integration problem, looking for that function, that somehow, getting rid of that derivative. So it's not such an unreasonable thing to do to say, hey, let's think back to when we were learning about integration, some of our good tools that helped us solve our more challenging integration problems. And the best tool, the number one tool when it comes to working with integration, is substitution. So our goal for right now is to say, hey, let's think about how we can use that idea of substitution to help us solve differential equations. Let's begin. So again, our goal is, hey, we're talking about substitution. So what are we doing? Well, we're going to introduce a new variable. Now, why do we do that? Well, we want to help simplify the differential equation that's involved. If you think about what substitution is in integration, it says, hey, we're going to introduce a new variable that helps us simplify the way we're expressing the integral that we have to solve, and simplify it so much that we might even be able to integrate now. Now, where do we want to simplify to? Now, what's our goal? Well, basically right now we have sort of two targets we can be shooting for, and that is we want something which is either separable or something which is linear first order. Now, why do we like those two targets? Because those are things that we can do. And it's possible that we can take something which is neither of those, and with a good substitution, we can end up with one that is one or the other. And that's what we're going to see. We're going to see several examples of different types of substitutions. We'll see some that are somewhat more common. Of course, we can't get them all. There's so many that are possible. But let's look at some common ones. And the first one that we're going to look at says, well, suppose we see something in the form ax plus by plus c, and it's showing up inside of functions. Now, what does that mean? Well, what we mean by that is the following. It says, hey, suppose we have something of the form y prime equals some function of ax plus by plus c. That's what we mean when we say it's showing up inside of functions. And so, all right, great. So what do? Well, we say, hey, that thing on the inside, because remember, where do we oftentimes look for substitution? Well, substitution, we oftentimes look for the inside functions, right? One way to think about it is that substitution is an inside job. So look on the inside. You say, all right, well, really, we want to take that whole inside expression and give it its own name. And so we're going to say, well, we're going to call this whole inside piece Z or Z, depending upon how you want to sound. Now, we want to be careful here because there's a lot of variables in place. We have x and y are both variables, and we have this new variable, z. So the question is, okay, well, how do we make sure we keep track of things? In other words, which variables are independent variable, and which ones are dependent variables? And generally speaking, if you have something on this form, where we have this y prime, we think of this as dy dx. And that dx part, that's telling us, hey, we should be thinking of this part. That's the variable we want to phrase everything in terms of. So in this case, we would say, all right, when we look at this expression, what we really have is z of x. And on the other side, we really have, look, this is ax plus by of x plus c. So that really everything is in terms of x. And now when we take derivatives, we take derivatives with respect to x, because that's telling us that's what we should be doing here. And so what happens? Well, all right, z prime of x, all right, which we would just denote as z prime. That would become a, b, y prime of x, right? Because that's what we have there. And the c is a constant, so it goes away. And in particular, it says, wait, we can replace our y prime by 1 over b, z prime minus a over b. Now, this is an important thing to do because remember, whenever we're doing substitution, there's a basic thing we have to do, and we'll write it down so we don't forget. So recall, when substituting, we have to substitute all the variables. And what does that mean? Well, we should really say all occurrences of the variable. Now, there is, of course, a little bit of subtlety here. which variable are we substituting in for? Are we substituting in for x, or are we substituting in for y? And in this case, we would say we're substituting in for the y variable. We're going to think of this independent variable as sort of just still floating around as needed. So what happens? Let's see what happens. We can actually follow it through. So we start off with something, well, it could be a little messy. It might not be separable or be linear originally, but when we carry out the computation, we say, well, it becomes, this expression looks like 1 over b times z prime minus a over b is equal to f of z. Or, well, what can we do? We can, if we multiply through here by, say, a factor of b, and then bring the a across, we can say, look, z prime is equal to b times f of z plus a. And now we're like, aha, this is good. This is good. Why? Because what do we have here? What is this? Take a look. What can you tell us? Well, this is separable. That is, hey, look. When you look at our situation, our z prime, that's dz dx. And so there's only one x part right there. We can move that across. We can move all this part with z across by division. And then we separated it, and we're off to the races. We actually have a chance. The only thing that might stop us is how good are we at doing our integration. But of course, you know, we're getting good at it, right? We can do it. Well, let's try an example. Let's see what happens. Okay. So here we go. Let's solve y prime equals 4x plus y plus 3 quantity squared. All right. Well, you might say, hey, do we need to do any substitution? Because, you know, just because we have a tool doesn't mean we always have to do it. And here, this is a case where, yeah, we kind of have to do something. It doesn't really work because it's not linear in terms of y, because you're going to end up with a y squared term here. It's not separable because the 4x and the y are together here. You can't really pull them apart. So let's do our substitution. And this is a case where we say, oh, look, there's this expression, 4x plus y plus 3, inside the square. All right, so that says this part here, that should be our new variable. We'll call that z. Okay, so what do we say? Well, we have that z is equal to 4x plus y plus 3. And we're thinking of everything depending as a function of x, because this derivative is by our convention, that's dy dx. So we're going to think everything in terms of x. So we're going to do our derivative in terms of x. And what do we have? Well, we have z prime is equal to 4 plus y prime. And now we can say, great. Well, what can we do? Now, here's something you might notice. And let's just point out really quick. We can save ourselves a lot of work because we say, hey, do we know what y prime looks like? And the answer is, yeah, see this? This is y prime up here. Y prime is this expression, but we can just say, what does it become? It becomes z squared. And therefore, we have, great, perfect. So this becomes 4 plus z squared. And now we're really in good shape because, well, what do? We say that dz dx is equal to 4 plus z squared, or divide by 4 plus z squared, dz over 4 plus z squared is equal to dx. And we've done our separation, which means we're a third of the way through doing our separable integration problem. We integrate both sides. Now this side is a little bit subtle, and so you would probably do some substitution. But it looks like arctangent, right? And so if you're familiar with this type of integral, you can sometimes jump and say, aha, we know what it is. I happen to have done integrals involving arctangent before, so I'll go ahead and write down what it is. But if you needed to, you could do a little bit of work and see, aha, this is 1/2 arctangent of z over 2. On the other side, well, we get x plus some constant c. All right, great. So now we can multiply and say, hey, this is the same as arctangent of z over 2 is equal to 2x. And then there's the 2c. But I like to just say, hey, constants absorb constants. And I just always like to update that. So every time I see a constant interacting with another constant, I say, okay, just sort of, absorb the constants together. And so I'll still write it as plus c. No, I didn't do bad math. I just had bad notation. Well, maybe they're not completely different, but all right. So let's keep going just a few more steps. We can get rid of the arctangent and say, all right, that's the same as tangent of both sides gives us z over 2 is equal to tangent of 2x plus some constant c. Or, we're getting really close, z is equal to 2 tangent of 2x plus c. Now, are we done? And why not? Well, we've done the hard part. We've done the integration. What haven't we done? Well, what we haven't done is put everything in terms of what we started with. We started in terms of x and y. We need to end in terms of x and y. So we say, well, that's no problem, because we can come over here and we can say what z is. So we say, okay, so 4x plus y plus 3 equals 2 tangent 2x plus c. And finally, we get y by itself. We can say, hey, y is equal to 2 tangent of 2x plus c, subtract 4x, subtract 3. And that's it. That's it. We're done. We did it. Wow. Amazing. Amazing. Isn't it great? We can do all these fun things now because, well, we have better tools. We couldn't solve this one without carrying out the substitution because we didn't have the technology. But by making a substitution, all of a sudden, life becomes great. It becomes wonderful, and we're able to make progress. And that's what we like. We like making progress. All right, well, let's look at something else that could happen. So, we say that a differential equation is homogeneous if it can be written in the form of y prime is some function of y over x. Now, that's kind of a strange way to define things, because you look at the word homogeneous, like, what? What does that mean? And what does it have to do with looking like that? Well, homogeneous has two key parts. First off, the homo, which means same. So it's saying something is the same. And of course, what's the same? Well, the other part's the same, which is the genius. But what's that? Well, so for that, I like to think of it in terms of polynomials. And so what do we have? Well, let me give an example here. You can imagine we have something like x to the 6 y prime plus 2x cubed y cubed is equal to 7x to the 4th y squared plus 18y to the 6. All right, so that's the expression. Say, okay, great. Now I ask, what's the degree? And you say, well, some of these aren't so bad. X to the 6, that's degree 6. Y to the 6, that's degree 6. Well, what do we think of these? And we sort of channel our inner Captain Planet. And we say, their powers combined. All right, so if I have a cube and a cube together, that makes 6. A 4 and a 2 together make 6. So you say, oh, when we think of these, they're all basically look like little pieces of polynomial, all with the same degree, same genius. So that's what it's referring to. Now, what happens? Well, if they all have the same degree, then by doing a proper division, in this case, divide everything by x to the 6, what you'll discover here is that something really nice happens. Namely, this becomes y prime. Here, you get 3 x's to cancel, so you have y cubed over x cubed. So that's the same as y over x cubed. And here, you can cancel 4 x's, so you get y squared over x squared. So that's 7 y over x squared. And here, you just have 18 of the y over x's to the 6th power. So that everything becomes in terms of y over x. So that's what it means. Now, that's not the only thing that can happen. There's other things that can happen. You might see something along the lines of the following. You might have something like the form, well, what about, say, y prime equals x plus the square root of x squared plus y squared. Well, whoops. There we go. It wasn't homogeneous, right? The problem was, what was the polynomial here? It was 1, which is degree 0. So I need to put something there. Okay. So is this homogeneous? Well, yeah. And I say, well, wait. Hold on. What about this part? Well, notice it's really like a square root of a square, which makes it more or less degree 1. And so you can imagine if you multiply everything by 1 over x, well, you'd have y over x, y prime. All right, that's that term, equals 1, which is fine. And then you can put the 1 over x into the square root. When it goes into the square root, it becomes an x squared downstairs. So x squared over x squared becomes 1, and y squared over x squared becomes y over x squared. And there we go, off to the races. Looks good. All right, so what do we do if we see one of these things? Well, we're channeling our substitution. Substitution says look for things on the inside. And we say, hey, I see something on the inside. I see this thing called y over x. Let's make that our substitution, right? Okay, let's do it. So we'll let z equal y over x. As before, we say, well, really what we have is this y prime is telling us take the derivative with respect to x. So we should think of everything in terms of x. So this says z as a function of x is really this y as a function of x divided by x. Well, all right, great. Probably the easiest thing to figure out is say, look, we know how to replace this. I also got to replace that because every occurrence has to be replaced. That's what we're referring to. So the y is going to be replaced. So I got to replace this y and that y. So, all right, cross multiply, y equals x times z, and now take derivative. Derivative of y is y prime. Then we have, product rule. Derivative of the first is 1 times the second, z, plus x times derivative of the second, z prime. All right, great. Well, what happens? What happens? Well, if we carry out this substitution, what do we see? Well, we see that y prime, that becomes z plus x z prime, will equal our f of z. All right. Well, what can you do? One thing you can do is you can take the z across. So I'm just going to do that really quickly here. And now, what happens? Well, what we have is, look, on this left-hand side, it's become x dz dx. And we can do the following. We can write this as dz over f of z minus z is equal to, right, because we bring that over by division, and it's equal to dx over x. In other words, this is separable. So, if we have something which is homogeneous, we can get to something which is separable, and modulo our abilities to do integration, that's something we can solve. So that says, hey, homogeneous differential equations are differential equations which, assuming our integration skills are up to the task, we can solve. Good. Well, we like things we can solve. All right, well, let's try an example. Okay, so here we go. Here we go. All right, so we have some problems. Solve the following. All right, 2xy dy dx equals 4x squared plus 3y squared. And then a separate one, y prime plus x equals the square root of x squared plus y squared. So there's two of them. Double the fun. All right, well, let's just start with our first problem. Okay, so what are we going to do? Well, first thing is we should rewrite it in terms of homogeneous. And we should ask, is it homogeneous? Well, yeah, because we see degrees. Here it's a 1 plus 1, that makes 2. 2 and 2. Everything's degree 2. So divide everything by x squared. So I'm essentially looking for the largest power of x. That should tell me what to divide by. Well, I really should say, look, everything's degree 2. Divide by x to that degree. So what do we have? We're going to have 2 y over x, and then y prime is equal to 4, x squared over x prime becomes 1, plus 3 y over x squared. All right. Now, at this stage, we're going to make our substitution, and we'll just make a little side note here. Our substitution is z equals y over x, and it's going to be the same for both, spoiler alert. And we can go grab our notes and just, no need to reinvent the wheel. Say, hey, what's y prime going to be? So y prime will be equal to z plus x, z plus x z prime. All right. So what do we get? Making our substitution, our first equation becomes, we have 2 times z times z plus x z prime is equal to 4 plus 3z squared. All right, well, we can distribute. So we're going to get 2z squared plus 2xz z prime is equal to 4 plus 3z squared. And we can subtract 2xz z prime is equal to 4 plus z squared. Like, ooh, that sounds really familiar, right? Yeah, maybe. Now we can do our separation. And we have, well, 2z divided by 4 plus z squared dz is equal to, and when that comes over, it'll be 1 over x dx. All right, well, now we've done our separation. Time to do our integration. So, integrate. Now here, that 2z upstairs changes our actual integration. Here we do a substitution. So we let u equal 4 plus z squared. And if we do that, we see, oh, hey, du is 2z dz, which means this becomes the integral of du over u, which is log of u, which is log of 4 plus z squared. Now, I'm not worrying about the plus c because there's going to be a plus c on that side. So we get that the natural log of 4 plus z squared is going to be equal to the natural log of x plus a constant c. Okay, well, almost there. And what can we do? Well, the easiest thing to do is to now raise both sides to a power. And doing that, all right, I say raise both sides, I mean e2 both sides. We get 4 plus z squared. Well, I come back, let's replace what z is. So that's y over x squared. Here, e to the log x is x, e to the c is a constant, and it'd be multiplication. So it's going to be some constant times x. And finally, to clean it up, let's just get rid of this fraction downstairs. Everything gets multiplied by an x squared. So that would give us 4x squared plus y squared is some constant x cubed. Now we could go a little bit further and say, okay, solve for y, and we'd get, we'd get two possibilities, plus or minus. Well, this is a wonderful way to express the answer. This is what we would call an implicit function. We'll talk a little bit more about that in a future session. So, there we go. Well, that wasn't so bad. Great. We have all this real estate left, which is good, because we still have a problem. So, all right, let's get to work. And, well, this is similar. We talked about this. One very similar to it. It says, all right, divide everything by x. And what will we have? We'll have y over x, y prime plus 1 is equal to the square root of 1 plus y over x squared. Okay, so we're still doing our same substitution because it's homogeneous, so it's always the same substitution that we carry out. So we're going to get z times the y prime becomes z plus x z prime plus 1 is equal to the square root of 1 plus z squared. Okay, well, let's subtract 1. So I'm just going to put that over there. And now we can divide by z. Okay. So put it divide by z. And then we can, here, well, that says now subtract z. All right. So we have that expression. Yeah. Let's see. We should probably clean that up a little bit, right? Yeah, we should. We should. Okay. So this is the same as the square root of 1 plus z squared minus 1. Actually, it becomes minus 1 plus z squared. Because if you see this, you have the minus 1. This will become minus z squared. All that over z. Okay. And now what? Well, that is equal to xz prime. So we now do our separation, which means we're going to flip this when we bring it over, and the x is going to come across. So we have ourselves z, and then we have a square root, 1 plus z squared, and, well, both of these have 1 plus z squared. So I'm just going to pull out a single square root of that, 1 minus the square root of 1 plus z squared. Okay, so that's this whole expression where I've pulled out a square root of 1 plus z squared on the inside. And let's see, what else do we need? Well, we have a dz. So, and that is going to be equal to the x will come across and the dx will come across. So it will come across as a dx over x. Now you might say, Steve, you left a really suspiciously big gap there. I have. The thing is, the downstairs looks very like something we don't want to deal with. And so we're going to try to find a way to not have to deal with it. So how do we do it? Well, let's clean this part up. And the way we can clean that part up is to say, you know, this I can multiply by the conjugate because that will help me get rid of the square root. So multiply by 1 plus the square root of 1 plus z squared. 1 plus the square root of 1 plus z squared. Now, what happens here? Let me carry out that multiplied by the conjugate. Notice that we're multiplying by 1, so it's still, at the end of the day, everything is the same as what we started with. So what's happened? Well, it'll become our a squared minus our b squared. So we get rid of the square root. In fact, we even get rid of more things. The 1's cancel, and so we end up with the minus z squared. And we already had a z upstairs, so we can cancel a single one of the z's. And so, where are we at? Well, so don't forget the minus. So we are at minus 1 plus the square root, 1 plus z squared. Divide that by downstairs, we have z square root of 1 plus z squared. Okay. Oops, not dx, dz. Excuse me. And we can separate this. So we say, okay, this is the same as minus 1 over z square root of 1 plus z squared. And then minus, in the second term, the square root of 1 plus z squared is canceled, and we have a minus 1 over z. Like, wow, that's great. That's lovely, right? Yes, yes. Well, we're running out of some real estate here, but you know what? In for a penny, in for a pound. Let's go for it. Let's go all the way. Okay, so let's see. We'll put some extra space here. Okay, so what do we have? Let's see where we're at. So we have now minus 1 over z square root 1 plus z squared dz minus 1 over z dz is equal to dx over x. Okay, so that's what we have when we clean everything up. Now, what's next? Well, integrate. And the good news is that 2 of these 3 integrals are very straightforward. So this will be log x, this will have minus log z, and this one will be interesting. All right. It's times like this that make you wonder, you really hope you did your math right, but I'm pretty confident. If nothing else, this is good practice for us. Do you remember how to do this kind of integral? It's strict substitution. So this is one where, because you see that square root of 1 plus z squared, it kind of feels a lot like that tangent, that arctangent. In fact, that's what we would do. Z equals tangent theta. And then we'd say, okay, great. 1 plus z squared, that's 1 plus tangent squared, which is equal to secant squared. And so the square root of 1 plus z squared is equal to secant. And the other thing, of course, we should say, what's the derivative of tangent? It's secant squared. So, updating, well, we have the minus, and then we have 1 over tangent theta. And what else do we have? Well, we have secant squared theta, square rooted, and so that means it's really secant theta. And then upstairs, whoops, I've got my d theta there, secant squared theta d theta. Well, we can cancel one of those secants right away. That's good. So what do we have? Well, we have secant over tangent. Now you might say, well, can that simplify? And the answer is yes, it can. All right, so how? Well, that's the same as, because secant is 1 over cosine, tangent is sine over cosine, it's the same as 1 over sine. And so, okay, 1 over sine, also known as cosecant. Now, what's the integral of cosecant? It is, because of that minus, this is one that you may not know, but it's very similar to the integral of secant. So it's log of cosecant plus cotangent. Okay, but now we have to work our way back. Well, what's tangent? Well, the tangent is z, so cotangent is 1 over z. How about cosecant? Well, cosecant, I have to be a little bit careful here because it's not exactly 1 over secant. That's not how cosecant works. So what can we say? Well, all right. So what we can say is that, just trying to think of the funnest way to do this problem. Okay. So, well, all right. Here we go. So we'll do our draw a triangle. We know tangent is opposite over adjacent, so square root of 1 plus z squared is hypotenuse. So the cotangent, adjacent over opposite, that's where the 1 over z comes from. Cosecant, well, that's 1 over sine. So sine is normally opposite over hypotenuse, so this part would be the square root of 1 plus z squared over z. All right, great. So that's what we have. And you'll notice that, of course, that's this expression. We have a minus log z. And so if we put things together, I should have added a plus z up here. We can actually combine that minus log z into that expression. And so what do we have? Well, we're going to have natural log of the square root 1 plus z squared plus 1 over z. Now that's just that part, but see that minus log z? I can combine it in here and say that turns it up to z squared is equal to natural log of x plus c. And of course, okay, take e to both sides, and we can say, great, the square root of 1 plus z squared plus 1 over z squared is equal to, here, we're going to get some constant x. Now, well, what does everything become? We replace z by our substitution. So recall that z is equal to y over x. So we have the square root of 1 plus y over x, quantity squared, plus 1 is equal to, well, we can move that z squared across, some constant x of y over x squared. Now, finally, multiply everything by an x. Why? Well, here, notice that you get one x to cancel, so there's still a single x not accounted for. So we're going to multiply everything by x, and if we do that, we're going to end up over here with a constant y squared, and over here, well, we'll have an x, and then we push the x into the square root, and so we're going to get x squared plus y squared. Good. Done. Done. Wow. You know, even if we made a mistake, what a journey. All right. Well, goes to show you, we have the technology, but we may have to work for it a little bit. All right. Well, let's try another problem. Another one. Of course. So make substitutions of the form x equals u plus h and y equals v plus k, where we think of u and v variables and hk constants, to solve the differential equation dy dx equals 2y minus x plus 7, 4x minus 3y minus 18. Now, it's sort of telling us, hey, make a substitution, so we know the substitution to make, but it's not really giving us a lot of direction. So for instance, it hasn't really said what h and k should be. So there's probably something that has to happen, because h and k are constants, which means they are choices. So at some point we're going to come to this and say, let's make a choice for h and k so that everything becomes somehow simpler. Now, we don't know at the outset what that means, but let's explore a little bit, and we'll figure it out as we go along. So there's a couple things that we can see. Well, since x equals u plus h, we see that dx would be du. And since y equals v plus k, we could say, well, look, dy is dv. And so dy dx is dv du. Okay, well, that's not so bad. That says, great. So we have dv du is equal to, over here, we're going to just replace y and x by what they are. So 2y, so 2 times v plus k, minus x, u plus h, plus 7. Divide that by 4 times x, which is u plus h, minus 3 times y, v plus k, minus 18. So if we clean that up, well, probably the thing to do is we put variables with variables and constants with constants. So that would be 2v minus u, those are our variables, plus, and there's this other stuff, 2k minus h plus 7. Downstairs we'd have 4u minus 3v, plus, then we have the other stuff, 4h and minus 3k minus 18. And now we say, okay, do we have inspiration for what we should do about our choices for h and k? Now remember, whenever we're working with a problem, our goal is simplify. Make things as easy as possible. We say, you know, the easiest thing to do is just to have nothing there. And so we're saying, you know what would be great is if it became that. So somehow that we could get rid of these last pieces. So the question says, is there a good way to do that? And, well, yeah. We say, look, we want to make these last two things 0. So our goal, we want 2k minus h. Well, I'll write it as h plus 2k. And, h minus 2k, excuse me, equals 7. So that's the same thing as saying that equals 0. And this one is the same thing as saying 4h minus 3k equals 18. All right. So now we have a classic 2 equations and 2 unknowns. Now this is kind of bread and butter. We're going to be doing this a lot. So we need to get really good at it and be comfortable doing it. So how do you do it? Well, generally speaking, you have 2 kinds of approaches. What are they? Well, you can solve for a variable and substitute, and that's a great way to do it. Now the other approach, and one that I'm a little bit biased towards, is to take what I would call linear combinations. In other words, we have these equations here, and we're going to combine them. But we're going to combine them in a smart way. And what makes it smart is we say we want to have things cancel. Well, so let's suppose I wanted to cancel the h's. I see I have 4 h's here. There's just a single h here. So if I multiply the first equation by -4 and then just combine it with the second equation, what would happen is that I'd have minus 4h plus 4h would make 0 h's. So in other words, I reduce down to fewer variables. And that's oftentimes the way you go about solving these things, is say, hey, you have a lot of unknowns. Well, get down to where you have fewer unknowns, and then fewer and fewer and fewer. So you just have, look, it's just one unknown, and here's what it is. And then we're like, oh, that's so good. So then we have plus 8k, subtract 3k would make 5k. Here we have minus 28, plus 18 would be minus 10. So we say, okay, that means that k equals -2. That's not so bad. And once I know k equals -2, I can come back to either one of these 2 equations. It doesn't matter which one. So let's say I go to the first equation. So h minus 2 times minus 2 is plus 4 equals 7. All right, so h should equal 3. All right, great. So now we've made progress. So we'll make some notes over here. So we actually know that the substitution we want is x equals u plus 3, that's u plus h, and y is equal to v minus 2, that's v plus k. So this is our substitution that we're making, and when we made that substitution, these pieces go away. They're gone. Oh, so good, so good. And now, what do we have? Well, if you look at our expression, 2v minus u over 4u minus 3v, we can do something here. Namely, we say, look, divide both top and bottom by the factor u. Or you can think of this as we're multiplying both on the top and on the bottom by 1 over u, which means multiplying by 1. So we get that dv du is equal to 2 minus u over v. Whoops. Sorry, I'm dividing by u, not by v. Okay, so that would be 2 v over u minus 1. And downstairs would be, we're dividing by u, so that would be 4 minus 3 v over u. And in particular, this is a function of v over u. So what do we have? We have, this is homogeneous, which is great. That means we can solve it. Now, it wasn't homogeneous before, because if you look at the top, see, you have some things which were degree 1, these pieces here, but then this is a constant, which is a degree 0 polynomial. So it wasn't homogeneous to start with, but by making a substitution, we got to something which was homogeneous. And now we have the technology. We just have to remind ourselves what the technology tells us. It says, okay, before we said, hey, when it was like y prime equals f of yx, well, okay, look, this is like v prime equals to f of v over u, but it's the same philosophy. Then our substitution, we're going to substitute the inside part, so, and then we'll get an expression. So here we go. Let's see what we get. So, wow, more substitutions. That's right. Because, you know, sometimes calculus problems are like onions. They have layers, you know, so it's substitution after substitution. They're also like onions in that tears may be involved by the time we reach the end. So we're making our substitution. Z equals V over U, or of course we can write this as V is equal to Z times U, or we have that V prime is equal to Z plus U Z prime. That's what it will come out to be. And so we have our V prime becomes Z plus U Z prime, and that's going to be equal to, on this other side, we're going to get 2Z minus 1 over 4 minus 3Z. Okay, so now it's a simpler problem, and we know this is going to be separable. We just have to do the work. So, all right, we subtract Z from both sides. So this is the same as 2Z minus 1, and then we're going to have minus Z times 4 minus 3Z, all that over 4 minus 3Z. Okay, well, that would be, let's see what we have. We'd have 2Z minus 4Z, and so that would be minus 2Z. Then we have a plus 3Z squared and a minus 1, all over 4 minus 3Z. Okay, and that's equal to, on this other side, we have UZ prime. So, where do we go? Well, it's separation. So we get 4 minus 3Z divided by 3Z squared minus 2Z minus 1 dz is equal to du over u. And we're ready to integrate. Okay, great. So, woohoo! Progress. Now, one of these two sides is going to be straightforward, and the other one is going to require work. And I think we all know which side is which. So yeah, the du over u, no problem. That's log of u. And we'll throw in our plus c. This side, let's get to work. So how would we go about integrating that? Well, one thing to note is that the denominator is actually kind of nice. They chose it well. And when I say they, the people who wrote the problem, in that it factors. So how does it factor? Well, it factors as z minus 1 and 3z plus 1. You can check. You get 3z squared, then you get plus z minus 3z, that's minus 2z, and then minus 1. All right, great. Exactly what we needed. Okay, so why is that good? Well, that means that we can use a certain type of machinery. In particular, we can use the ideas of partial fractions. All right, so here we go. We're going to do some partial fractions up on this one. So let's grab a new pen here. So we're going to start by saying, well, look, 4 minus 3z divided by z minus 1, 3z plus 1, looks like something over z minus 1 plus something over 3z plus 1. All right, because that's how partial fractions works. And clear your denominators. 4 minus 3z is equal to a times 3z plus 1 and plus b times z minus 1. Now, there's a couple of different philosophies of what to do next. I personally like the philosophy, make good choices. You know, it just sounds like great life advice. Make good choices. And so what that means is choose values for z that help simplify the expression dramatically. So what are some good choices? Z equals 1 is a wonderful choice because that will knock out the b term. So we're going to get 4 minus 3, which is 1, is equal to a times 4, 4a. Or, great, a is 1/4. Now another great choice would be z equals minus 1/3. Why? Because that'll knock out the a. You get minus 1 plus 1, gone. So 4 minus 3 times minus 1/3 really becomes 4 plus 1, which is 5. Now, then we're going to get minus 1/3 minus 1. What's that? That's minus 4 thirds, right? Minus 1/3 minus 1. It's minus 1/3 minus 3 thirds. That's minus 4 thirds times b. Or, you get that b is minus 15/4. Ooh, that's a bit of a doozy. Okay, but the good news is we can now say, look, our integral is the same as 1/4 times 1 over z minus 1, then minus 15/4 times 1 over 3z plus 1. And that integral is one we can actually carry out. So we'll end up with 1/4 log z minus 1, and then minus, and it's going to become log of 3z plus 1. And be careful here. We have the 15/4. Because there's a 3 here, we have to account for that. And what will happen is, at the end of the day, the way it gets accounted for is it'll come in as a 5/4. Because you're going to divide by 3 to account for that 3 there. All right, so great. Well, we're actually in pretty good shape, because remember, this is the left-hand side. And we know that, what that equals. We can clear out our fractions. We can say, all right, that's the same as log of z minus 1 minus 5 log 3z plus 1 is equal to 4 log u plus c. Again, that c absorbs a constant. Okay, well, now we take both sides, raise it to the power e. And what can we do? Well, this 4, we'll throw it in as an exponent. And so on the right-hand side, we're going to end up with a constant, because we have e to a constant becomes a constant, u to the 4th. On the left-hand side, what will we get? Well, what we're going to have is this part will be upstairs as a z minus 1. And then this part will be downstairs because of the minus, as 3z plus 1. But again, because of the 5, that comes in as an exponent. So it'll be 3z plus 1 to the 5th. All right. Whew. But what is z? Z is v over u. So we really have, this is v over u minus 1. And downstairs we have this is 3 times v over u plus 1 to the 5th. And if we're careful here, which of course we're always careful, right? Yeah, of course we are. Of course we are. Let's push this up a little bit here. Then what happens next is, well, we'll get a, on the upstairs, this is the same as 1 over u times v minus u. And downstairs, well, this is going to become 3v plus u to the 5th, right? Because I can get a common fraction of u. And then I can pull out that 1 over u to the 5th. And so what happens is, if we follow this through, this part right here, 1 over u to the 5th, is like we have a u to the 4th. And what do we have over here? U to the 4th, which means that those parts cancel. They're gone. So we say, aha, this is really beautiful. So we end up with v minus u. We'll go ahead and move that across. That's equal to some constant c times 3v plus u to the 5th power. Now, here is where we have to go back and say, well, wait, what is everything? So we have to go back here and say, well, look, we know what things are. So x is u plus 3. So I'll make some notes here. X equals u plus 3. And y, well, what is that? That's v minus 2. So another way to say this is, hey, u is x minus 3, and v is y plus 2. So if we look at our pieces here, and don't worry, we're almost done. If you're thinking like, this problem is never going to end, it's going to end in just a few moments here. All right. So if you look at v minus u, what do we have? Well, that's really y plus 2 subtract x minus 3. So this becomes y minus x plus 5. All right, so that's this piece. And then 3v plus u. Well, 3 times v, that's 3 times y plus 2. And then plus u, which is x minus 3 again. So we're going to get 3y plus x, and then we have 6 minus 3, which is plus 3. So our final answer, because we want a final answer. We've put in our work here. We deserve to get a final answer. V minus u, we write y minus x plus 5 is equal to some constant c times, and 3v plus u becomes 3y plus x plus 3 to the 5th power. Wow, that's an amazing problem. An amazing problem. But if you look at it, okay, yeah, we did a lot of work. You know, we have to go back and remember, where did the problem start? It started here. dy dx has this form here, and we were able to get an expression. But the individual steps, no step was too hard once we knew what we were doing. And it had to nudge us and say, oh, make a substitution. And the idea was, oh, make substitutions to help us get rid of the constants. So we figured out how to get rid of the constants. And then we said, oh, hey, now we have something which is homogeneous. So we did something which is homogeneous. Oh, partial fractions. Okay, carry out the partial fractions. And then just work on unraveling at the end. So we got everything in terms of x and y. So yeah, a lot of parts in this problem, but every part was something we can do. So yeah, wow, we are making amazing progress. Just think, we couldn't have done problems like that a few weeks ago, and now we can. All right, well, let's try another problem. A Bernoulli equation is a differential equation which can be written in the form of y prime plus p of x times y equals q of x, y to the n. So the key here is this, we have this other side here, where you have y to a power. Now, if this was y to the 0, great, we can do that. That's linear first order. If we just had y to the 1, well, yeah, we can actually do that too, because we could subtract it across, and we have something separable. So it's like, oh, you can do it for n equals 0, you can do it for n equals 1, can you do it for others? And the answer is yes. Yes, we can. And so we have a technique, and then we call these Bernoulli equations. And what's the substitution? Well, it's not so clear. This is a case where it's like, oh, there's not something on the inside, so what do we do? And they say, look, here's the substitution to make. y to the power of 1 minus n. Now you might look at this and say, what? How? Where did that come from? And we'll see how it works in just a moment here. But let me just comment that if you're like, wow, this seems very unintuitive, well, yeah, there's actually a clue that it's kind of an unintuitive thing. Do you see how it has a name? Bernoulli? Well, usually when you see something with a name attached, that means, wow, there's like a challenge here. This is something highly non-trivial, and so we need to, indicate it, and honor the person who came up with the solution, or at least came up with a good chunk of it. And so you don't see easy problems with names. It's not like, some person named Greg added 7 and 12 and got 19, and like, wow, that's amazing. Let's call that Greg's number. No, easy problems don't get names. Hard problems do. So don't be discouraged if you're like, I don't know if I were to come up with this substitution. Well, you're not supposed to have. But somebody did. And you might wonder, well, how did they do it? And the answer, they tried a lot of stuff. And the stuff that worked, they told other people. The stuff that didn't work, well, they probably threw into the fire. And they probably had a lot of material to throw into the fire, because that's how progress is made. Lots of trial and error with mostly error, but the rare successes. So, well, okay, great. So we have our substitution, and we say, all right, taking the derivative of z, it's derivative of z, and now we have to use the chain rule. 1 minus n comes down, subtract 1 from the exponent, becomes minus n, and then derivative of y. Okay, so let's see what happens to our equation. So we started with y prime plus p of xy equals q of xy to the n. If I divide by 1 over y to the n, this becomes 1 over y to the n, y prime, plus p of x, this will be y to the 1 minus n, and that'll equal q of x. Now, some good news is we say, hey, some of these pieces look pretty straightforward. This y to the power of 1 minus n, that's exactly what z is. Great. That's easy for us to replace. And this term right here is actually that piece right there. And so, we say, well, now we say, well, that is almost z prime. It's just this one factor here. So this becomes 1 over 1 minus n z prime. And if we stare at this and say, hey, that looks really very close to a linear, first-order linear differential equation, it's because it is a first-order linear differential equation. In particular, what this becomes, if you multiply by 1 minus n, you get z prime plus 1 minus n p of x z is equal to 1 minus n q of x. And we say, aha, great. We have the technology. We can solve this. And off we go. Off we go. So that's the idea. Of course, then there's the actual, let's try it, and let's see what happens. So let's try some examples, and let's see what happens. So we're going to do 2 examples. So let's start with our first example. We have xy prime plus 6y equals 3xy to the 4/3. Now notice, what's the form we want? Well, we want it to be y prime plus p of xy, q of xy to the n. So we want to make sure what's in front of the y prime is 1. But notice that here, this y to the 4/3, that falls into the y to the n. We can have strange exponents. It doesn't have to be a whole number. So we're allowed to have a fractional part of a number. Nice. All right. Well, let's see what happens as we move forward. So, well, let's not worry about the x. We know what our substitution is going to be. So we're going to start here. So we're going to let our z equal y to the 1 minus 4/3. Right? So z is y to the power 1 minus n. And here we have 4/3 as our power. So we say, okay, great. Well, what is that? Well, that's y to the minus 1/3. Then we have z prime. Well, that's negative 1/3 y to the minus 4/3 times our y prime. All right, so if we come through here, we're going to take our equation, and I like to divide everything by y to the 4/3 just to help us follow through what's going to happen. So we're going to have x y to negative 4/3 times y prime plus 6y to the minus 1/3 is equal to 3x. So this equation right here takes our first equation and divides everything by y to the 4/3 power. And from here, we just carry through our substitutions. So the y to the minus 4/3 y prime, this is going to have become minus 3z prime, and don't forget the x. So minus 3xz prime. Here, y to the minus 1/3 is going to become z. So there's a plus 6z, and the 3x will become 3x. Yes! Ha ha ha! Oh, I like it when things are really easy to work with. All right, so now divide by 3x. Divide by negative 3x, so you get c prime is the first term. Then we're going to get minus 2 over x z equals minus 1. Okay, great. Well, that's going to be pretty straightforward, won't it? Yeah, we like it when things are pretty straightforward. Okay, well, what happens? We need to do our integrating factor. So our integrating factor is going to be here's our p of x, so we're going to do e to the integral of minus 2 over x. All right, well, that's the same as e to the minus 2 natural log of x. Remember here we don't need to worry about the plus c when we're doing our integrating factor, which is the same as e to the natural log 1 over x squared, which is 1 over x squared. So we're going to multiply through by 1 over x squared, and when we do that, we get that we have 1 over x squared z prime minus 2 over x cubed z is minus 1 over x squared. But the left-hand side, by design, this is how our first order linear equations work, it's a derivative of a nice thing. It's the derivative of 1 over x squared times z. And that's minus 1 over x squared. And now we're ready to do the next step. And our next step says, hey, we're going to integrate both sides. So integrate with respect to x. So if we do that, well, what do we have? We have 1 over x squared times z. That's the left-hand side. And the integral of minus 1 over x squared is actually pretty straightforward. It's 1 over x. And then, of course, plus some constant c. Well, we're almost there. We're almost there. Let's go ahead and multiply through by x squared. So we're going to end up with z is equal to x plus some constant x squared. But we got to go back and say, what is z? That's y to the minus 1/3, which is the same as 1 over the cubed root of y. All right, well, now we can flip both sides, and we can say the cubed root of y is equal to 1 over x plus some constant x squared, or finally we get that y is equal to 1 over this x plus a constant x squared cubed. And we're done. We're done. Whew. Okay, well, that wasn't too bad, but we made the substitution, became linear, used the tools for solving those linear, and life is good. Life is good. And we still have some space. So on now to the other one, right? Because there's 2 bullet points, so we're going to do 2 problems. So that way we can be twice as good. Well, maybe that's how it works. Now here, notice this y squared is kind of saying it doesn't quite look like the right thing yet, but remember there's this word can. Bernoulli equation can be written in that form. So you might have to do some gentle massaging. And, well, okay, let's do some of that nice gentle massaging. So this can be written as y prime plus 2xy is equal to 6x y to the minus 2. So that says that we should choose n to be minus 2. All right, well, that's fine. So what's our substitution that we're going to be making? Well, we're going to choose our substitution is z is equal to y to the power 1 minus minus 2, which means z equals y cubed. Like, wow, that's nice. That's the kind of substitution we like. Nice, positive, whole numbers. The kind of substitution we'd like to go and bring home to meet our parents during our next school holiday. So z prime is 3y squared y prime. All right, and we say, hey, wow, it's set up exactly for what we need in the original. So we don't even have to do really anything. And so we'll just go ahead and just make those substitutions. So y squared y prime will become 1/3 z prime. All right, that's the first term. 2xy cubed will become 2x times z. And 6x will become 6x. Yeah. Funny how that works. Okay. Well, now we can multiply through by a factor of 3. We can say, look, z prime plus 6xz needs to equal 18x. So this is our p of x. So let's do our integrating factor. And what do we have? Well, our integrating factor is going to be e to the integral of 6x, which becomes e to the 3x squared. Okay, so we're going to multiply on both sides. So we're going to get e to the 3x squared z prime plus 6x e to the 3x squared z is equal to, on the other side, we're going to have 18x e to the 3x squared. And, well, the left-hand side, by design, is the derivative of e to the 3x squared z. And we say, okay, so really, it's just a matter of working on that right-hand side. Left-hand side's easy. Right-hand side, well, might have to work a little bit, but probably not too hard, because otherwise we'd be in trouble. And in this case, we don't have to work too hard, because you can see there's a substitution. This is almost a substitution we can do in our heads. And so in the interest of space, I'm just going to say out loud what happens. If you let u equal 3x squared, du would be 6x dx. So we only are off by a factor of 3. So that becomes 3 e to the 3x squared. That's the integral. Don't forget your plus c. And so finally, well, not finally, but we can now divide by that e to the 3x squared, so we get that z is equal to 3 plus some constant c e to the minus 3x squared. All right, are we done? And why not? Well, we're almost done. What is z? Z is y cubed. So this equals y cubed. So our final answer, we say, look, y is the cubed root of 3 plus some constant c e to the minus 3x squared. And And now we're done. That's it. See? These aren't so bad. These aren't so bad. I mean, they're non-trivial. You got to work. But at the end of the day, we can do it. And isn't that nice that we can do it? All right. Well, let's look at some other cases. So we've been talking about first-order differential equations, but we can also talk about second-order differential equations. And we say, okay, is it possible to reduce, right? Because it says, second order, it sounds twice as hard as first order, actually probably more than that in most cases. But it turns out that there are some special cases where when our expression of our differential equation is kind of missing pieces, we can say, oh, we can exploit that to help us reduce down from second order to first order. So what do we mean? So we'll talk about two cases. So suppose we have a second order differential equation where it's of the form f of x, y prime, y double prime. Now when you see this right here, you might think of something very complicated, but really you should see that statement and say, oh, it's a statement, some combination, which involves x, y prime, and y double prime. And they say, oh, wait a second, there's no y. Oh, let's use that. So there's no y term, and so we say, okay, great. We make a substitution. We'll let z equal y, and then z prime equals y double prime. And so what we really have is we really have a first order differential equation that in terms of z. And of course, once we solve that, we just say, look, but then once we know what z is, we know that's y prime, and then we just have to integrate again. So that's pretty straightforward, no surprises. All right, but something else can happen. Suppose we have a second order differential equation where it's some expression which involves y, y prime, and y double prime. This time there's no x. Okay, then you make the substitution, and we're going to call it z of y is y prime. Now I'm emphasizing something here, which you might notice, but may not register right away, is I really want to think of this as a function of y. If you come back up here into this first expression, we didn't even really say it out loud, but we should, just because something weird is about to happen. We're really thinking of this as functions of x. So z prime of x equals y prime of x. But because there's no x term showing up in the original formulation here, we're going to say, oh, our goal is to figure out what is y prime in terms of just y. So we're really shooting to say, okay, we're going to think of y prime as being some function of y. Now, what's going on here? Well, notice we have this statement here. Z of y times z prime of y equals y double prime. Now, you might say, wait a second, hold on, that doesn't seem right, because if I take a derivative of y prime, that's y double prime. If I take a derivative of z, that should be z prime. Where does this show up? All right, hold that for just a second, but let's just assume that this is reasonable. Then what happens is, okay, our y prime becomes z, our y double prime becomes z prime, and lo and behold, great, we can find this formulation for z, first order, and we have z, which is y prime as a function of y, and we can solve. If we believe this part. So I want to talk for a few seconds about why that's not so crazy. And it all boils down to thinking about this inside piece. Do we think of it from the perspective of y, or do we think of it from the perspective of x? And that's why there's this small difference going on. So let's think about what y double prime is. Y double prime, well, we think about it as the derivative of y prime with respect to x. Okay, so far that's not very surprising. Okay, that's fine. That's good. But the key here is when I think about taking the derivative of z, where do I want to take the derivative with respect to? I don't want to take it with respect to x, because I'm thinking of z as being a function of y. So there's the subtlety. I want to think of z as a function of y. So we say, all right, great. what we can do is we can say, by the chain rule, I can then multiply this by, well, let me be careful here. So if I want to look at our z of y equals y prime, and now what I'm going to do is I'm going to take the derivative of both sides with respect to x. All right, well, on the right-hand side, that's no problem. We get y double prime. On the left-hand side, well, chain rule says you take the derivative of the outside, and then you multiply it by the derivative of the inside, which is dy dx. Okay, well, what is dy dx? It's y prime. So that becomes z. So that's what's going on. So y double prime is equal to z times z prime. All right. The moral is don't think too hard if this is stressing you out. We'll do an example in just a few moments that says, hey, let's do it in two different ways and just compare to convince ourselves, yeah, there probably is something going on here that says you really do need it this way. All right. So here we go. Here we go. So we're going to solve the following. So x squared y double prime plus 3xy prime equals 2. Now, what's happening here? Well, there's no y, but there's x's and y primes and y double primes. So we're going to let z, and just to emphasize what's going on here, z as a function of x is y prime. Or we have z prime is y double prime. So we say, hey, this is the same thing as x squared z prime plus 3x times z equals, x times z equals 2. And that's a linear first order. Well, divide everything by x squared. We'll get z prime plus 3 over x times z is equal to 2 over x squared. So here is our p of x, and we compute the integrating factor. And so the integrating factor, that's e to the integral of p of x, which is e to the integral of 3 over x. Well, that's e to the 3 natural log of x, which of course the 3 can come in as an exponent, making this x cubed. So everything gets multiplied by x cubed, so we get x cubed z prime plus 3x squared times z equals 2x. Well, the left-hand side, that's not so hard to see, that's the derivative with respect to x of x cubed z, and that should equal 2x. And we want to integrate both sides. So we're going to integrate both sides with respect to x. And what happens? Well, we end up with x cubed times z is equal to x squared plus some constant c, or z, and let's just remember z is y prime. Y prime is x squared over x cubed, 1 over x, plus some constant c over x cubed. Now, integrate. And what do we get? Well, we'll get that y is log of x plus, now, normally if you integrate something over x cubed, what would we get? Well, that's x to the minus 3, and when we divide by minus a half. But there's a constant there. So what can we do? We can absorb that in. So this will become plus some constant over x squared and plus another constant. So there we go. And notice that we do end up with two arbitrary constants, which we should. When it's a second order differential equation, we should have two constants showing up. Essentially, you should think about every time you take a derivative, you lose a piece of information. And so when you work back up, we need to have the ability to gain two pieces of information, or if you like, to specify two pieces of information. So there we go. There's that one. Now, the other one. Okay, we'll do this one twice. So first off, let's do it without any substitution. This y double prime equals 3y prime squared. Notice we can rewrite this by doing a little bit of moving around. So I'm going to move the y across, and I'm going to move a single y prime across. So that this can become y double prime over y prime is equal to 3y prime over y. So everything's still there. I've just moved things around a little bit. And you might say, well, why did you do that? Well, this is something that you can actually integrate without much work. Because you see we have a function and derivative. Function and derivative. And when you see that form, function downstairs, derivative of that function upstairs, it becomes natural log. So we can say, look, the natural log of y prime is 3 natural log of y plus some constant c. Raise both sides into the exponent, and we can say, oh, this is the same as y prime. So the 3 can go in, and then the e to the constant, making sense. This is some constant, y cubed. All right, so that's y prime. All right, well, great. Now, we're not yet done, because we still have to say, well, what is y? But now we can say, well, look, right, this says y prime, or if you like, think this says dy dx. You say dy over y cubed is equal to c dx. Integrate both sides. And what do we end up with? Well, dy over y cubed would be minus 1/2 y squared. And that should be equal to some constant, y to the minus 2, excuse me, because you have y to the minus 3, so when you add, it'll be minus 2, and you get cx plus some constant d. But I can multiply through by minus 2, absorb those constants in, so we can come to the conclusion 1 over y squared is equal to some constant x plus d, and now flip both sides, take a square root, and we say, aha, y is 1 over the square root of some constant x plus the constant. All right, so that is the second one without doing any kind of substitution. Now let's do the substitution we were talking about. And so remember, that one is the one that's kind of interesting. We're saying, okay, we're thinking of z as a function of y, and that's being our derivative. And so the second derivative is that z times z prime. So let us see what happens. And beforehand, what should be true? What should be true is we should end up with that. If we don't, uh-oh. We'll edit that out. That's what'll happen. That's what'll happen. All right, so here we go. So remember, z is going to become y prime, and z times z prime is going to become y double prime. So the y stays as y. So we're going to have y, then we have a z prime is equal to 3, and then over here we're going to have z squared. All right. So, well, we can cancel off a single z. So we have z prime times y equals 3z. And remember, this z prime is dz dy, because we're thinking of z as a function of y. That's the key. Now it's not a function of x, it's a function of y. So this we can do separation. So we can say, look, dz over z, I'm bringing that z across, is going to be equal to, and on this side we're going to get 3 over y dy. So that's separation. We do our integration. Log of z, well, that becomes 3 log of y plus c. And, well, okay, raise both sides to the power e. And what do we see? We see that z is equal to, and again, this becomes a constant y cubed, or what is z? Z is y prime. So you get that y prime is equal to a constant y cubed. And now we are back to right there, which means we'll end up at the same place. So yeah, it worked out. So it does work with this kind of weird, crazy substitution. Well, maybe we should say this counterintuitive substitution. But yeah, life is good. Life is good. All right. Well, let's mention one more thing, and then we'll call it a day. So the last thing is to talk about this. It says, hey, there's lots of substitutions. And so don't try to focus on memorizing every possible substitution that there could be, because you just can't do it. There's lots of them out there. Instead, you learn to focus on finding good substitutions. Now, where do you find good substitutions? If you think back to calculus, when we first learned about substitutions, there's essentially two places to look. So one is look for something on the inside function. And this is our tongue-in-cheek, substitution is an inside job. But, oftentimes because of the place it came from, it came from the chain rule. And so we said, we look for a function on the inside, and that gives it away. But there's another place to look, which is if you go back to substitution, we would say, hey, look for a derivative. And what does that mean? Well, what that refers to, if you think about the formula for substitution, we would have f of g of x times g prime of x dx. So the inside is saying, look for the g of x. Finding the derivative says, hey, do you find something that looks like a derivative? And so you can look in either of those two. We've mainly focused on saying, hey, this thing is on the inside, and we did a substitution. But the next two examples are going to be, hey, let's look for derivatives, and let's see what happens. All right, so here we have some examples. And on the first one, I just want to point out, you have this part xy prime plus y. And we look at that and say, hey, wait a second, we've seen things that look like that. That's a derivative. And in particular, we say, wait, this looks like the derivative of xy. So, with that in mind, we have sort of our aha. Let's make that our substitution. So, since that's our derivative, we say, okay, our substitution that we're going to make is we're going to let, we'll let our variable, call it z, is x times y. And now we're going to replace all of our pieces of y. So we're thinking of y as z as being an x. So we can say, hey, I can replace y by saying that's the same as z over x. So if we carry this substitution through, what happens? Well, this will become the following. We have the y squared becomes z over x squared. And we're going to get the derivative with respect to x of z, which really means we have dz dx. And then we have that square root of 1 plus x to the fourth. And over here we have an x. Now, we're able to actually rearrange everything because we have a z squared here and then a dz equals. There's an x squared, there's an x, so that'll become an x cubed. And then we have what else? We have this square root of 1 plus x to the fourth will come across, and it'll come across as 1 plus x to the fourth to the minus 1/2, because it's a positive square root, so it comes across, 1/2 power here comes across as minus 1/2 power, and then the dx. And now we're like, well, great. We can do this. This is just a nice separation. We've done the hard part. And so let's see what we have. Well, what we get, we'll get 1/3 z cubed. And that'll be equal to, well, from here, if you do some substitution on this one, u equals 1 plus x to the 4th, we get that 1/4 du is x cubed dx. Or really, we'd say du equals 4x cubed dx, but I could see there was an x cubed there. And so say, okay, well, this would become the integral of 1/4 times u to the minus 1/2 du. And so, well, that's 1/4 u to the positive 1/2, then times it by a 2. And of course, add a c. And so we have, we ran out of space here. So this will be 1/2 the square root of u, which is the square root of 1 plus x to the 4th, and then plus constant c. All right, now that's all equal to 1/3 times z cubed. So, well, what is z? That's x times y. So, updating, I'm going to multiply through by 3, and then I'm going to replace z by xy. So x cubed y cubed is equal to 3/2 1 plus x to the 4th plus c. Now that says y cubed is equal to 3/2, whoops, I forgot to write to the 1/2, 1 plus x to the 4th to the 1/2 plus c, divide that by x cubed, and finally we can take the cubed root and we come to our conclusion that says, hey, y is, well, you can take the cubed root separately on top and bottom, the cubed root of 3/2 1 plus x to the 4th to the 1/2 plus c, and downstairs over x. And done. Great. Wow. Cool. So that one, not so bad, right? Not so bad. Well, one last one. One problem to help bring it home. Finish it up. And let's see. I'm pretty optimistic. I think we can do it. Okay, so we're probably going to need some space here. Now, looking at things, one of the things that you might say at the beginning is, well, how do we start going? One of the things I see here that jumps out is I have an e to the y and an e to the minus y. I would not want them to have different exponents. It's like comparing apples to other kinds of apples. It's not ideal. So what I'd like to do is somehow make everything in terms of e to the y. And we can do that because, look, this e to the minus y is the same as 1 over e to the y. So if I think about it that way, we can say, look, this is really the differential equation, x plus e to the y times y prime is equal to x over e to the y minus 1, which seems a little bit more fair. I don't like my fractions. Within frac, so I'll multiply through by e to the y. And we can say, hey, this is the same as x plus e to the y times e to the y, y prime, is equal to x minus e to the y. And now you might say, hey, look at this piece. When we look at our y's, they always are seeming to show up as e to the y's, right? There's e to the y, e to the y, e to the y, other than that y prime. And that e to the y, y prime, what can we do with that? Well, we say, hey, this part right here looks a lot like the derivative with respect to y of e to the y. So this is our great, so we make the substitution, z equals e to the power y. And if we do that, well, then what we really have is that this is our z prime. All right, so let's go ahead and see where this takes us. So we're going to have, with this substitution, x plus z times z prime equals x minus z. All right, well, we've already made it simpler, which is the goal of substitution. And in some sense you could say, okay, as far as substitution goes, we're done with the problem. But you know, we need more practice. And how would we go about solving this one? Do you see what it is? It's homogeneous. And in particular, we can say, look, divide everything by x. So this becomes 1 plus z over x times z prime is equal to 1 minus z over x. So that everything really says it's functions of z over x. So we're going to make another substitution. That's right. This is an onion problem. A substitution within a substitution. Layers and layers. Oh, this is good. Let's see. Well, we've already used z. Let's see. Well, we've already used y's and x's. W, right? X, Y, Z, W. That often seems to be the way it goes in mathematics when we need the next letter. So W is going to be z over x. And we say, well, look, that's really the same as z equals x times w. Well, that gives us that z prime is going to be w plus x w prime. Okay, so now with this substitution, what do we have? Or what are we up to? Well, we're up to 1 plus w, that's this piece, times z prime, which is w plus x w prime, that's the z prime, is equal to 1 minus w. Okay, well, yeah, let's keep going and we'll see what happens. So that's going to distribute through, and we're going to get w plus w squared plus x times 1 plus w times w prime is equal to 1 minus w. Well, move this piece over. So we'll have x times 1 plus w, w prime. Well, 1 minus w minus another w. So that's 1 minus 2w plus w squared. But aha, that factors. Nice. That's 1 minus w squared. Okay, so moving things around, which by the way, I should have said it's the same as w minus 1 squared. So we're going to move that across. We'll get 1 plus w divided by w minus 1 squared dw is equal to, and then the x dx moves across, 1 over x dx. Now, we've done our original substitution, it was homogeneous, new substitution, rearranged, we're well into our separation, and we're ready to do our integration. And you might say, how do we do this? Well, this is where things get interesting. Now, on the left-hand side, we really should do partial fractions, but there's kind of a shortcut here. Say, well, look, the downstairs looks pretty good. Let's make the upstairs look like w minus 1's things. So how do we do it? Well, look, this w plus 1 I can think of as w minus 1 plus 2. And this probably is not the first thing you might think of, but it doesn't mean it's not right. And because we've made things look like w minus 1, so we can say, well, look, this is really 1 over w minus 1 plus 2 over w minus 1 squared. All right, well, great. Well, both of those pieces are things we can actually integrate. So 1 over w minus 1 would become log of w minus 1. And 2 over w minus 1 squared, whoops, I forgot my dw here, would become what? Well, it would become minus 2 over w minus 1, and that's going to equal log x plus a constant c. Now, I don't know if it really gives us much advantage to get rid of the logs, because this term doesn't have a log in it. But we should say, well, what is w? W is z over x. Well, what is z? Z is e to the y. So what we should say is, where you have that w is equal to e to the y over x. So putting that in, we say, hey, this is really log of e to the y over x minus 1, and then minus 2 over e to the y over x minus 1 is equal to natural log of x plus c. Now one could go through and do a little bit of cleaning up, but there's not really a lot of cleanup you can do here that really makes it meaningful. So we will just instead be happy with what we have, which is we have an answer and life is good. We put in a lot of work today because, you know, even after substitutions, there's work to do for integration problems. These take time and takes lots of practice. There's a whole course, you know, advanced calculus, calculus 2, which is all about, hey, how do you get good at doing integration? And the answer is do lots of problems. So it was good for us to do lots of problems today. All right. Well, I think the next few sessions hopefully won't be quite so bad. So we're through the thick of it in some sense. And look for good days ahead. All right. See you later.